finish our notes from yesterday, and then I'm going to introduce the last, I'll call it a project. It's not a big project, and I'm going to give you some groups to work in, and then I'm going to attempt to get you into breakout rooms with your groups so you can kind of divvy up the work. Hopefully some of you had a chance to look at the requirements regarding the 6 simple machines. You can use that document today to go through with your group and divide up the work. So hopefully we get more folks showing up. I also attempted to send private messages to anybody who owes me stuff. So on Edmodo, be checking your messages. And if you need to hang out after class to get any questions addressed, please do that because time is winding down. Let's jump back into our notes from yesterday. We should be on Roman numeral 2. Did anybody have any questions from what we put into our notes yesterday? We kind of came to an abrupt halt. You can either type your questions or ask them aloud right now. Anything coming up?
On the last blank, for demo, less distance makes work blank blank. I didn't get those two.
Yeah, so the concept of using the simple machine known as a ramp or an inclined plane lessened the amount of input force. So we said that less force makes work seem easier. It's kind of an illusion because the amount of work that you end up doing with or without the ramp ends up being about the same because we have to overcome friction and we're doing the work over a longer distance, but it makes the task seem easier because this value here, this variable of F, force, is lessened, and that's the
Okay.
big key. That's the big point, and that's something that you'll hopefully find out about the simple machine that I assigned to you. The whole job, or I'm sorry, the whole idea behind using a simple machine is that they do this. They lessen the amount of input force over a longer distance so that you can accomplish some work. Good question, Noah. Any other questions? So as we look to the final part of our notes, we're going to emphasize input and output. Capital letter A, work input, is simply the work you put into a machine. And it's calculated by multiplying your input force by some distance. So anytime we see a reference to input, it's the force or the work that you're doing. It's the force or the work you're applying. And then the opposite of that is work output. That's the work and the force done by the machine. Hopefully by now, I keep saying hopefully because it's so hard to gather definitively. Hopefully by now you have an understanding of how to calculate work. Work is force times distance, and we express it in joules. As some of you still turn in or make corrections to the powerful workout calculations and conclusions, we're still confusing work and power a little bit here and there. Work is found by multiplying force by distance. And when we get a Newton of force by a meter of distance, we get joules of work. Any questions on any of the blanks that we have here?
Can you fill out the work output blanks?
Yeah, so how would we calculate the output work or the work output, the work done by a machine? What two variables would we need to know?
Wouldn't it also be force and distance?
Right, but what word are we going to put in front of the word force this time?
Machine force?
Let's use the word output, because output is referring to the machine. Output is what the machine does for you. Input is what you do. So right now, this might all be a little bit vague because we haven't applied it to any specific machines. But that's what you'll be in charge of once we get into this last part. Ignore these bold lines here. I don't know what those were for in the original notes. I would not, however, ignore the highlighting. We're going to make more of a point to emphasize the idea of input force and output force. Input force and output force are critical for finding out the effectiveness of a simple machine, which is what we're going to transition to next. So unless I hear otherwise, I'm going to scroll down the page. I'm going to get to the last part of our notes, which is called mechanical advantage. Mechanical advantage is a calculation to allow us to see how good a simple machine is. Mechanical advantage is a number that tells us how many times a machine multiplies our input force. Mechanical advantage is how many times a machine multiplies our input force. And it can be found by dividing the output force by the input force. And it's one of the rare instances where we get to calculate something and express a final answer without any units. Because when we divide output force, which has units of newtons, by input force, also in newtons, newtons over newtons cancel. So we're looking for values greater than 1. Anytime we have a mechanical advantage on a machine that is less than 1, it's not a very good machine. What would it mean if we calculate a mechanical advantage of something like 0.5? What is that machine doing?
Less work than what you're doing.
Let's keep it to force, but I agree with the idea that you shared, Preston. Let's just put it to some values. Give me an output force value, Michael. Make up a number.
10.
Okay. So if the machine gives us 10, what would our denominator value have to be to result with this answer? Brian.
Could you repeat the question, please? Sorry.
Michael told us that the machine gave us 10 newtons of output force. My question is, what would the input force be resulting in this answer of 0.5?
5?
No, 10 over 5 is 2. Try again. Yes, you do. 10 over what equals 0.5, Brian?
I don't know. My brain's kind of.
Okay, I'm not letting you go on this one. Switch it on. 10 over what number is equal to 1/2? 10 divided by what number equals 0.5? Try it out on a calculator.
Yeah, I don't know what to put in the calculator.
Joe, help him out.
10 over what number is equal to 1/2? Wouldn't it be 20?
Yeah, absolutely it would be. Brian,
Yeah.
can you see that? 10 over 20 is equal to 1/2?
Yes, sir.
Okay, I want to bring it back to the point of mechanical advantage. If the machine does, if the machine does 10 newtons of force and you're doing 20 newtons of force, what's wrong with that? Brian, could you tell me on that one?
You're doing more work than the machine.
Let's again keep it to force, but yes, I agree. You said something very similar to what Preston said. You're doing more force than what the machine gives you. That means it's not a very good machine. That either means there's a lot of friction involved, or it's just not worth the use. You can accomplish the task without it. So what kind of numbers should we look for here? Bringing it back to the point. Jackson? I can tell you right now that if your video is off, I'm more likely to call on you because I can't tell if you're paying attention or not. But Jackson, tell me, what kind of numbers do we want for mechanical advantage? Jackson, are you there? You could type an answer. How about Cole? Cole, are you with us?
Yeah, but I don't. Yeah, but I don't know.
Okay, that's okay to not know. We just said that numbers less than 1 means that the machine gives you less force than you put in. So what numbers should we look for? What numbers would be good for our mechanical advantage?
A number higher than 0.5?
Well, yes. So even a number like 0.9 is going to tell me that the amount of force that I put in is greater than what the machine is giving me. Like, tell me this, Cole. I think we can get to this. What would our output force and input force be like to get us an answer of 1?
They would have to be equal.
Yeah. So if I put in 10 and it gave me 10, then my mechanical advantage is 1. So that's okay. So I'm going to again ask the question, what kind of numbers do we want for mechanical advantage? Jackson, are you with us? Paging Jackson. How about, anybody? Anybody unmute yourself. Let's get moving on with this.
Wouldn't it be any number greater than 1?
Yes, good. Maybe that's a note that you add beside this statement here, that any mechanical advantage that is more than 1, we can just simply say it's a good machine. That machine is multiplying your input force. That machine means maybe you put in 10 newtons and we get out 20. Okay, guys and girls, that does wrap up our notes. Hopefully you're gathering from my tone through a screen that it's pretty strict. I've noticed that in this last week, there's kind of this thing going on like, yep, I'm done. I'm mailing it in. and it happens whether we're in normal school, and it seems to be really prevalent in digital school. So from a teacher point of view, the need to be stern is still very much there. We don't want to mail it in 3 days before the end of an early out kind of end to the school year. My point is finish strong, guys and girls. You're probably hearing that from many of your teachers, finish strong. Questions on anything that you see in the notes or any blanks that remain? Because now what we're going to start to do is transition to this. I heard somebody pipe up. Question?
Yeah, so the like black I don't know, bracket thing.
Yep.
Is that just formula? Like what we put on the little line?
Yeah, it could be the formula. There may have also been a reference to efficiency, which is work output divided by work input, but I'm not going to get too caught up in efficiency. The big thing that we'll look at for simple machines is this mechanical advantage. So output force divided by input force.
Okay.
Good question. Any other questions? Before I give you some groups. So here's what I'm going to do, unless questions come up. I'm going to assign you two things. I'm going to assign you a group and a simple machine. The groups will consist of people from math and general math and honors math mixed together. Every group has 4 people except for a couple, I think there's 2 groups that only have 3. The biggest thing I want you to try and accomplish today is just figuring out what part you'll be responsible for. So if we look at this list of requirements, there's a Google Slides presentation, and there's simple things that you can do together, like a title page, a definition of what the machine is, its job, and then a statement of the force distance trade-off. This is something I referenced yesterday, and also something that I kind of, well, answered Noah's question with. It's this idea here that when we use a simple machine, less force over a longer distance makes work seem easier. That's that force distance trade-off. The biggest thing with this project that I want you to know is that you're responsible for one thing, whether it's the diagram drawing. You can hand draw something, or you can find an appropriate diagram or drawing from the internet. Real world uses and examples of that machine, and then reference to mechanical advantage. You're responsible for one part, and I'm going to grade you on that one part. And I want to just try and ease your minds that I'll grade you for the one part that you did. If you have somebody in your group that either isn't present or doesn't do anything, don't worry about that person. I'll grade them independently of what you submit. Any questions on that? So while we're compiling things together in a group format, you'll still be graded individually for the part that you do. And I guess the other thing that is worth sharing is that this isn't going to be some gigantic make or break kind of project. So don't freak out that for many of you, the hard work that you've done in distance learning, it's not going to come down to one project where it'll be make or break. So this is really meant to just be kind of the last thing and a chance to work together on something. So unless there's